Good morning everyone. Today we are going to see the introduction to search methods applied to robotic systems. Before getting into the search methods, we will see the outline what we are going to be studying in this course or in this lecture. First we are going to see the introduction to search methods and their importance, their evolution, and then the major two types of search methods, which are breadth search method and depth search method, which is precisely breadth first search method, depth first search method, which involves first in first served, last in first served approaches are involved here. Okay, so let us see the search methods involved in robotics. Search algorithm. Search algorithms are algorithms which enable robotic systems to navigate or locate paths effectively in their work volume. The importance or the significance of the search methods are for tasks such as obstacle avoidance, exploration and autonomous navigation, and it directly impacts a robot's efficiency, safety and reliability in dynamic environments, where both the obstacles as well as the targets vary with respect to time. Now coming to the evolution in search methods, the early influence started in the year 1959, where breadth first search method and depth first search method were formalized as part of early AI research, building on graph theory concepts by researchers like Edward and Claude. Then we see the heuristic search that is developed in the year 1968, which is a popular technique called A* algorithm by Peter Hart, Nils Nilsson and Bertram Raphael at SRI International, marking a significant advancement in informed search. Then the modern integration started in the year 1990s onwards, where the integration with AI leading to adaptive search algorithms, and the contributions made by Stott, Russell and Peter Norvig in their book Artificial Intelligence, a Modern Approach, shows a significant growth of search algorithms with the integration involving AI is shown very well there in that book. Now the key milestones associated with search methods are development of SLAM, that is simultaneous localization and mapping, incorporating search methods with contributions by researchers like Sebastian and Huff. Then coming to the fundamental formulation of a search or planning problem. Before entering into this formation or formulation of the search problem, we need to define certain parameters associated with this formulation of search algorithm. First we define state. We know that it is a distinct situation for the world which is represented by a vector x or by a term x. So the state space is formed by the possible states forming the state vector space, and the actions, means of transforming the world, denoted by u. That means through this action the system will have the transformation of state from one state to another state, say from x1 to x2 state, and this transformation is represented by a state transition function, say f, that is providing the information of new state by taking the current state and current action as its input, and thus the state transition functional equation is given by x dash equal to function of the current state and current action. Now having the action, there is a action space which is nothing but the set of all possible actions over all states. Thus the action space is represented by u, which is equal to the union of all u of x, where x is a state which belongs to the state space x. Here u of x is the action space particularly for the state x. Now let us talk about goal states, which means the desired states for which each we are applying the actions through the search and planning algorithms, and it is denoted by xg, which is a subset of the state space X. Now let us see the example in formulating a search or planning problem. So the problem statement goes by this: a robot moves on a grid with integer coordinates. We have a grid for the robotic system, and let us say the robot is located in the center, which means let us say it is 0, 0 is the location of the robotic system. Then it has to move either up, down, right or left depending on the grid locations. The grid locations are nothing but the states. The robot is moving to different state which are nothing but the locations represented in this 2D grid. So, here in this schematic we see a state transition graph. It represents the movements as transitions between grid points. So, the mathematical formulation goes by this: the state space is a set of all grid points which are nothing but the integer pairs where I and j belong to the integer space Z. The action space here is nothing but the set of all possible movements obtained through the action u, where u, capital U, is the set of points go up from the current location, go down from the current location, go right and go left. These are the actions which are coming under the set U, which is called action set U or action space, you can say, formed by various actions to navigate and reach particular grid points. So, the state transition equation is now given by f of x comma u is equal to x plus u, where x belongs to the state space and u belongs to the action space. The initial state for the robotic system on the grid, say here it is taken as the origin 0, 0 is the initial state, which means the initial position of the robotic system. The goal state can be given as a grid point, which can be a single point or set of target points. Serially it can be reached first, second, third, fourth and fifth, or a single target point. Now, understanding the systematic search, there is something that we must understand: the term systematic in search algorithm. Systematic search ensures all reachable states are explored, which is critical for determining the existence of solutions in finite or infinite state spaces. Here we mostly use the graph search algorithm, where the state transition graph is revealed incrementally as actions are applied, not as a complete one. The complete map will not be revealed in the beginning. The map is getting explored incrementally as the robotic system moves from one state to the another state, and it gets incremented. The systematic search in finite graphs, we will see that now. And it is important to ensure that the algorithm avoids infinite loops and redundant exploration. That is in the case of finite graphs, because we must make sure that finite graphs based systematic search ensures the algorithm is avoiding infinite loops and redundant or excessive exploration of the same state point or the location. And it should also guarantee that the algorithm explores every reachable state in the state space. And this way, this algorithm can determine in the finite time whether a solution exists or not. Now, let us see the systematic search in the graphs involving infinite graphs. Here systematicity requires finding a solution in finite time if it exists. If the solution exists, then we need to find the solution in finite time. That is the systematicity expected in the infinite graph based search algorithm. So, we relax our requirements for systematicity by allowing the algorithm to search indefinitely if no solution exists. Here one requirement is that every reachable vertex must eventually be explored as the number of iterations increases. And this algorithm is continued with the assumption that the number of vertices are countably infinite, even though we say infinite, which could be countably infinite in this infinite graph search algorithm. So, let us see this schematic. Figure A indicates from the initial state it goes towards the solution in one direction, and due to which most of the space around this state or the reaching direction is undiscovered. Hence, the systematicity is compromised in figure A based search, unidirectional search. Whereas, in figure B we can see that from the initial state the search is happening in all direction through wave fronts, could be circular wavefront or square wavefront. It spreads. So that in all directions the goal or the solution is searched from the initial state. So, this type of search through wave fronts ensures broader coverage and no state is revisited in this case, and hence this type of search through wave fronts is systematic. Now, let us talk about the general forward search. At any point during a search there are three kinds of states. During the search there are three kinds of states. One is unvisited, as the name indicates, these are the states that are not being visited yet. Initially it is every state except the initial state xi. Now, there is another state called dead state, which are the visited states, but visiting and recording them or exploring them will not provide you any information. And there are alive states which are nothing but the encountered state, but possibly has unvisited next neighboring state. These alive states are stored in priority queue P using a priority function. Again, these alive states are stored in priority queue called P, which is an array, using a priority function. The only significant difference between various search algorithms is a choice of this priority function. How we can save or arrange the queues or queues of the states. First in, first out is one basic option. FIFO, first in, first out is one basic option here to have this choice function priority. In, first out, states are processed in the order they are added into the queue or the priority queue P. Now, coming to the general overview of this algorithm. First, we start with the initial state. That means P starts with the initial state xi, and there is a termination condition that we must also set, where the while loop continues until P is empty or a solution is found. Next, there is also failure scenario where P becomes empty without finding a goal state. P array where all the elements of this array getting explored, but we could not find a solution. So, it is a failure scenario. The failure scenario in infinite graphs is such that the algorithm may not terminate if a reachable portion of x is infinite. That is also we must consider. Now, let us have the pseudo code or the algorithm. First, record and then remove the highest ranked state x from the queue P, that is a priority queue P. Check if x is a goal state. If yes, report success and terminate the process of searching. Expanding the state for each action that belongs to the action space U of x as the input, that is the state x as the input, compute the next state x new, which is equal to the function of the current state and the current action. Then determine if x is unvisited, insert x new into the P array, that is a priority array, else skip x new since it is either dead or already in P. Now, let us see the particular forward search methods, which are nothing but the breadth first search method or depth first search method. There are two methods which we are going to see. The first one is breadth first search method. The concept here is it explores all the states at the present depth level before moving on to states at the next depth level. That means, if it is initial state, it will search here, and when it is coming here, it will search here again before moving to the next state level. So, it will search here and then it takes the direction, go up, go next, then search exploring here fully, then go up, then search. So, this is the way, this is the concept utilized here. So, it explores all the states at the present depth level before moving on to states at the next depth level. So, the priority queue follows this scenario, which is first in first out. So, the algorithm here is first initialize the priority vector or array P with initial state xi. While P is not empty, record and then remove the highest ranked state, which are nothing but the oldest state. Check if it is a goal state or x belongs to xg set, that is xg goal set. If yes, report success and terminate, or expand the state x and add universal state unvisited states to P. I repeat, if not, expand state x and add unvisited states to P. Now, let us see the example. So, we have the grid with the initial state being x 0, 0, that is point is the integer point is 0, 0, which is the grid point initial state, and the goal state is 2, 2. So, the exploration order here is it starts from 0, 0 and then goes to 0, 1, then 0, 2, that is it starts from here. So, this is x, this is y, starts here, then goes here, then it goes 0, 1, 0, 2, then it moves here 1, 0, then 1, 1. So, accordingly, right, then it moves. So, like that, then it reaches the 2, 2. All right. So, this is the exploration order in this case, that is the breadth first search approach. Then let us talk about the depth first search method. Here the concept is explores as far down a branch as possible before backtracking. So, the priority queue here is last in first out, that is the priority queue strategy, LIFO, that is last in first out. So, the algorithm states like this: initialize P priority vector with initial state x I, while P is not empty, perform this, record and then remove the highest ranked state, mostly recently added state. First do with that because it is LIFO based strategy. Check if it is a goal state, that is x belongs to the goal set xg. If yes, report success, expand the state x and unvisited states to P. So, the example here is having the grid with the initial state 0, 0 and the goal state 2, 2. So, here you can go in this manner, that start from 0, 0, then move to 1, 0, then 2, 0, then 2, 1 and 2, 2. So, this is faster as compared to that of the breadth first search method. Now, coming to the A star search method. So, the concept here is combines the cost to reach a state with a heuristic estimate of the cost to reach the goal point. Cost plus heuristic estimate of the cost to reach the goal, not only cost, not only the heuristic approach, combination of both cost as well as the heuristic estimates of the cost will help to reach. For example, here is the goal, we can reach this one, this one, this one and then go here, go here, go, or go here, go, then come here, this and this reach. So, this approach tells us to reach in this fashion. So, instead of reaching this way to the goal or this way to the goal, A star method tells us to reach in this fashion to reach the goal point, which means a combination of cost as well as the heuristic estimate. That is the motto of or the idea of A star search method. So, the priority queue states that states are ordered by f of x, where f of x is a function that is given by g of x and h of x. It is a combination of g of x and h of x. As I told, it is a combination of cost as well as heuristic estimate of the cost. So, g of x is the cost from the start state to x and h of x is the heuristic estimate of the cost from x to the goal. The algorithm for this A star approach is as follows. First, initialize the priority queue P with initial state xi with f of xi equal to h of xi, because initially your g of x is 0. So, while P is not empty, while the priority queue array is not empty, record and then remove the highest ranked state, which is the lowest of f of x. Check if it is a goal state, that means the current state belongs to the goal state vector. If yes, report success and expand state x and add unvisited states to the vector P with updated f of x. Now, again coming to the grid example. So, the example here is we have the initial state 0, 0 and the goal state again 2, 2. Here we use the heuristic Manhattan distance, which is similar to the Euclidean distance. And here the exploration order is from 0 to 0, 1 comma 1, 2 comma 2. So, we have this grid 0 0. So, reach here, then reach here, because it is a combination of okay, that gives your strategy, which is both cost as well as the heuristic of the estimated cost will help you to have the action to move from one state to the other state, and hence you can reach the goal state much effectively with less time. Now, coming to the comparison of breadth first search approach, depth first search approach and the A star search method. Now, coming to the, let us see the breadth first search method, the exploration strategy is level order exploration, where all nodes at depth d are expanded before nodes at depth d plus 1. Here the completeness is indicated in such a way that complete in finite state spaces, finds the shortest path in unweighted graphs, and the optimality is that it guarantees the shortest path in unweighted graphs, thereby ensuring optimality. The space complexity here is high, as it stores all nodes in the current depth, and due to space complexity we have time complexity, that is given by O of BD, where B is the branching factor and D is the depth of the shallowest goal. Now, let us see with the depth first search approach what happens there with these metrics. The exploration strategy here is deep exploration, goes as far as possible down one branch before backtracking. That is why the name depth first search algorithm. And the completeness, when we see the completeness of this algorithm, not complete in infinite spaces or with infinite paths, can get stuck in the loops. Now, coming to the optimality metric, this algorithm will not guarantee to find the shortest path, and it depends on the order of exploration. Now, the other two matrices, space complexity is low here, because it stores only the path from the root to the current node instead of storing so many states. And the time complexity is O of B power m, where B is the branching factor and m is the maximum depth of the search. Now, coming to the A star search, the exploration strategy in comparison to the breadth first and depth first strategies. So, here it is cost plus heuristic based exploration, and thereby it balances exploration and exploitation. And coming to the completeness metric, we can say that complete if the heuristic h of x is admissible, that is never overestimates the true cost. And coming to the optimality metric, it guarantees the shortest path if the heuristic h of x is admissible and consistent. And coming to the space and time complexities, the space complexity is very high because it stores all the nodes generated, and the time complexity is given by O of BD in the worst case, but often more efficient than breadth first search approach due to heuristic guidance. Heuristic guidance makes this A star search algorithm effective as compared to the two other search approaches. And with this, I thank you all. By this I can say that we have concluded this lecture in a way that we have studied the introduction to search algorithms, the history, how it is evoluted, and then we have seen the importance of search algorithms, and finally we have seen three algorithms which are nothing but the breadth first search algorithm, depth first search algorithm, and then A star algorithm, and we have compared also. Thank you so much.